What's going on, YouTube? It's that time again. It is time for another topic review as I'm working my way through the curriculum at the Flatiron School's Data Science Bootcamp. If you're new to this channel, if you're new to this playlist in particular, backstory. I am a student at the Flatiron School at their data science, in their data science program. It's a coding bootcamp. If you're unfamiliar, check the link below if you're interested or curious about it. 5 phases. I'm in phase number 3 right now, and there's about 10. I think this particular module, maybe 11 or 12, about 10 to 12 different modules in each phase. I just finished module 26, and as a new sort of study practice for this phase, I'm vlogging about my what I'm learning in each module as I go along through the phase. So like I said, I just finished module 26, and I have 5 more to go. It goes up to module 31, something like that. So anyway, this phase, or this module at least, is all about logistic regression, very similar to the last phase, and we're just diving a little bit deeper into that. The last few study vlogs, I've basically just I've organized the notebook in my own words or thoughts rather, versus this notebook or this module for the study vlog. I took a little bit of a different approach. I took the learning objectives that are like listed in the notebook for the labs, for each lab in the module, and I used those to kind of guide how I designed the notebook on this for this study vlog. So it's pretty verbose. There's going to be more code to show in this notebook than the last one. So yeah, we'll see how it goes. It's a little bit experimental, but that's what data science is, right? A lot of experiments. That's what science is. So anyway, let's move over to our Jupyter notebook. Whoops, let me get to where y'all can see the notebook right now, but I can't see it. Now I can see the notebook. Excellent. All right. Here's our module 26 topic review. So I was using this. This is like a markdown cell, right? So it's not an actual code cell. So because of that, I can't collapse these cells the way I normally have done in the past vlogs. So I'm just going to scroll through here real quick to show you like the broad topics that we're going to cover. And then we'll go through them a little bit more granularly. So first thing we're going to go over is visualizing confusion matrices, and obviously like explaining what a confusion matrix is. We're going to talk about evaluating logistic regression models and the type of metrics you got to use for that. Obviously we have code examples of how to implement those metrics. We're going to talk about what a ROC curve is, and AUC, score or value, whatever you would classify AUC as. Some example code again. We're going to talk about how to compare different logistic regression models against each other in order to pick the best one. All right. We're going to deal with a little bit of class imbalance, and or talk about what that is and how to deal with it. And if you're in the notebook, if you're looking at this on the GitHub, then here is a link to the GitHub, as well as the YouTube, the LinkedIn, if you want to connect with me on there. And here's a link to Flatiron School's website if you're curious about the program. So, confusion matrices. Confusion matrices. So what a confusion matrix is I don't know why I don't have, y'all are gonna see me do a little bit of HTML live. In these markdown cells, you can use some HTML elements to do stuff. There's a visualization that I thought I had in here. So if you're wondering, what I'm doing right now is I'm creating an image element, which this is all HTML code right here. And this is the file path to where the photo is. So you see that I'm in my study vlog directory here. Let me close that. And within that, I have this directory titled images. So we're kind of starting with, it already knows it's implicit that we're in the current working directory. So then you pass in the next directory that you want to step into, and then if there's another like folder you're trying to get into, you know how file paths work. And then at the very end, you're going to have the actual file handle that you're wanting to call, and you got width and center justification, like all that sort of stuff. Boom, there it is. So this is a kind of broad or like general example or visualization of what a confusion matrix is. So a confusion matrix is a visualization method that you use to evaluate binary classification model. Well, no, okay, any sort of classification model, because there are confusion matrices that you can have, you know, umpteen different classes that it plots the data for. But we're not going to go into that today, because right now we're focusing on logistic regression models, which is a binomial classification sort of thing. But this is like the basic idea here. It plots out, you know, you're classifying things as like true or false, positive or negative, and this is plotting the ones that your model predicted as true or false versus the ones that were actually true or false. So this gets you some idea of how well your model performs. And from this, we can calculate different metrics that we'll talk about later to actually quantify from this data how well your model is performing. So here's a little Python code on how to create a confusion matrix from scratch. So the first thing we're doing, obviously, we're defining a function here. Nothing really riveting there. The first thing that I did was I instantiated a empty dictionary. Well, it's not completely empty because we have our keys here and we have values, but they're all set to 0. The next thing, this y true and y predicted. It's important to note that for this function, if you're going to actually use this code, you would need to already have your model built and have fitted the model and with your data, your training data, you've done your train test split, all that stuff, and you've made your predictions from the training data or the test data, depending on like kind of where you're at in the workflow. But point being, this y true and y pred for prediction, that's all coming from your modeling workflow that you've gone through. So this code right here is kind of assuming that you've already sampled your data into training and test samples and built your model and fitted it and that sort of thing. So that said, these elements or variables, iterables that you're passing in are more than likely Pandas data series types. So to make things a little bit easier to deal with, I go ahead and I just change each of them to a vanilla Python list. Reason being, when you do your train test split, it's going to kind of scramble the indexes of each element, but it's going to preserve the index of each element. So you might have so the problem I ran into was like for like y is true. The first element in the series, the index position was like 253 or something like that. So I wasn't able to index it with this for loop here so easily. So the easiest thing to do is just change it to a list. If you're dealing with extremely large amounts of data, like, plus 10,000 rows or something like that, that might not be the most performant way to do things. But it worked for me for this module. So anyway, I'll quit rambling. We'll get on here. So this for loop is just saying like for each element in a range that is the length of your data that you're passing in. And of course, your y true and your y predicted is going to be the same length, so you shouldn't get like a index range error or anything like that. So we have this if statement is covering the true predictions, whether it's positive or negative. These predictions were actually the correct predictions, and the else statement captures everything that was an incorrect prediction. And of course, the nested if else statements under each of those are for the positive and the negative cases. We're appending, I guess, or we're adding the value of 1 to these zeros in this dictionary for every occurrence that goes through here. So as you're going through, you're iterating through your range that's created. So it's important to note that the for loop isn't actually iterating through the data that you're passing in directly. We're just capturing what is the length of the data that you're passing in, and we're basically kind of creating like a dummy list that is the length of that, and we're iterating through every element of that. So if you're curious about that, just look up Python range function, and that should kind of clarify that for you if that's seeming a little funny. So yeah, if y true is the same as y predicted, meaning it was an accurate prediction, then we do this. And if it's not the case, which we could do like the exclamation point equals, but the logic flow is the same if you just use like an else statement. Anyway, so for every one of these conditions that's passed, we go through each element and we check it against each one of these conditions. Once it captures or satisfies one of these conditions, then we add a 1 to this dictionary, and then it moves on to the next iterable in the range function that we've created right here. So, and this is an example of what your output would look like. You would get a dictionary, and it would give you like some amount of that's not 0 for your true positives, your true negatives, your false positive, false negatives, so on and so forth. So that's a lot of work, and like I said, if you're dealing with big data, this specifically this part where I'm like changing the data series to lists might not be that effective. So Scikit-Learn has a tool for this exactly from the metrics module. There's a confusion matrix function. Excuse me. And same thing, we're passing in our true, like the actual observed data. So this is y true. This was from this code snippet that I have. This is the actual like variable name of like the data that I was dealing with. And this is the predicted data. Again, this is predicted from the fitted model. So it's a lot of Scikit-Learn that happened like before this too. Anyway, this function is pretty simple. You pass in your observed data and your predicted data, and it spits back out at you a confusion matrix as such, but in the form of a NumPy array, which is probably in a data science pipeline easier to or better to deal with than just a simple dictionary like this. Of course, it would be possible to rewrite this to spit out a NumPy array instead of a dictionary. But anyway, so just a couple examples. Confusion matrix from scratch. If this was really just good for kind of learning like exactly what a confusion matrix is doing and like the logic behind it. But realistically, in the real world for like a real project, I'm just going to use the Scikit-Learn function. Likewise, there is a Scikit-Learn function for plotting the confusion matrix. So it's important to note this is not a matplotlib function. This is a Scikit-Learn from the metrics module function. It's just plot confusion matrix. So they're both in the same module at least. Pretty simple. So again, this is all this code you're seeing is assuming that you've already built your model and fitted and everything. So model log was the variable name of the model I was dealing with when I was writing this code. So, and then you're passing in your X test and your Y test. So your test samples, not your training samples. And you use call plot.show. This is, I'm assuming, built like on top of or with matplotlib, because plot.show shows the plot. So anyway, that's how you write a confusion matrix. If you're trying to be a nerd and you want to do it from scratch, that's how you do it. If you're just trying to get your project done, this is how you do it. And either way, if you want a visualization to communicate about your findings, this right here. All right. Evaluating logistic regression models. This is where the math's going to get pretty nifty. So there's a few different metrics that we use to evaluate logistic regression models. Precision, recall, accuracy, and this cool thing called an F1 score. So precision is, I think of it as the likelihood or the probability that any single given observation is correct. I don't want to say accurate because accuracy is another metric, so I don't want to confuse my terms here. So precision is basically the probability that any single predicted data point is correct, right? We calculate that. The math behind it is the number of true positives divided by the number of predicted positives. So this is a pretty simple function that I wrote in one of the labs that calculates precision for you. Again, this is assuming that you've built a model and fitted it and everything, and that's how you're getting your y-hat here by using your model.predict function in Scikit-Learn. And this is a list comprehension that we're summing up. We're adding a 1 to the list for every correct prediction for true pos here, and then false pos is we're adding a 1 to the list for every incorrect prediction. So, and then we sum all that up. It's a whole list of ones, so you sum it up, and that gives you the raw numbers you need to do your math here. And this return line is the formula that you see here next to precision. Your true positives divided by your true positives plus your false positives, your total number of predicted positives. And we make that a float here just to make Python happy. So recall, I was just talking with my cohort leader earlier about this. Recall was like weird. Just like the wording of it just kind of like didn't make a whole lot of sense to me. Your formula is your number of true positives divided by your number of actual total positives. So it's a little different than precision. So what really made it like click for me when I was talking to my cohort leader earlier, let's say you have 100 observations and 25 of them are true. We'll call it true, right? And let's say the model predicts that 50 of these 100 observations are true, and those 25 ones that are the 25 observations that are actually true are within that 50 that is predicted to be true. Even though its predictions are only right half the time, its recall would be very high because every single prediction that's actually true, the model did accurately predict that particular observation. So recall is a little funky in that sense. It's probably the least intuitive metric of the 4 that we're dealing with here. But my intuition is that it's probably one of the most informative. And your whole, like, when you're tuning a model and you're building your pipeline and everything, it's all this dance of kind of deciding which one of these metrics is really the most important to you. So if it's the most important to you that you don't miss any of the interested classes, but it's okay if you incorrectly predict some of the classes that you're uninterested in, then recall is probably what you're going to be focusing on the most. Accuracy is the proportion of total observations that are predicted correctly by the model, both positive and negative. So of all the predictions made, what percentage of them were actually correctly predicted? So you calculate that by taking your total number of true positives plus your total number of true negatives. So all of your correct predictions and divide that by all of the observations in your data. So accuracy, like I remember from physics in school, accuracy and precision was always this weird thing. So precision is more about any specific observation or any individual occurrence in the data, and accuracy is more concerned with kind of the aggregate of the data. So the accuracy is like what proportion of the predictions are correct, and precision is like what's the probability that a single prediction is correct. So they're related, obviously, but a little different. And again, we're using very similar kind of control flow here in our functions. We're zipping together we're zipping together our data that we're passing in, and that's going to give you a list of tuples using that zip function. Sorry, we got the laundromat, or the laundry. What am I thinking of? Landscaping guy outside. Laundry. Okay. So yeah, recall, precision, accuracy. Again, same thing. We're using that zip function. We're creating a list of tuples with that, and then we're indexing the tuples in that list and seeing if they match or they don't. And then we're actually using those sums to execute our formulas here on the return line. You're seeing this y hat here. That's the same as like up above where you saw like y predicted, wherever that was. Yeah. So hat is just like the mathematical term for prediction. So in LaTeX syntax, which you've seen me type in LaTeX before. I think you do that. It's just a markup language for, yeah. I'll make that a little bigger. LaTeX is just a markup language for like mathematical notation. So that's what, like, how y hat would be written like by hand. And obviously you don't type in LaTeX in Python, so you just do y underscore hat. But that's just like your y hat's just your predicted y values. So an F1 score represents the harmonic mean of precision and recall, which basically means that for your F1 score to be high, both your precision and your recall must also be high, which is pretty difficult to achieve, you might imagine. The formula for it's pretty simple. We're just taking a constant 2. Some really smart person figured out that a long time ago, I guess. And anyway, you're multiplying that by the precision times the recall divided by the precision plus the recall. So within this function, we're calling these other functions here. So if you were writing this all from scratch, you wouldn't directly call any of these functions, but you would be writing them just so that they could be called within your F1 score function. So you calculate your precision, you calculate your recall. I'm kind of breaking the pip8 rules here by capitalizing the P and the R, but I just wanted to because they're variables and not classes, but I wanted to distinguish them from the precision and recall functions. So anyway, you got your numerator, declare that, your denominator, declare that, and then you're running that formula on your return line. I am going to close the window real quick because they're weed eating like right outside my door or window. That's much better. Woo! Rolly chair. Okay, so that's your F1 score. Depending on what your goals are and what you need the model to what you need out of the model that you're building, you're going to focus on one or the other of these. So, for example, if I have 100 observations and only 2 of them are true. Making sure I'm not mincing my words here. So you want, and you're concerned with predicting those observations that are okay. Let me start over. You have 100 observations. 2 of them are the class that you're interested in predicting. The other 98 are just the complement to that. You're not interested in predicting those classes correctly. Like if you predict correctly, if you predict the other 98 correctly or incorrectly, doesn't matter to you. But those 2 classes, we'll call it class 1. Everything else is class 2. The class 1 observation data points, like it's important that you correctly predict those. All the class 2 data points, you could care less. In that situation, you're going to want higher recall, but versus like your accuracy or precision may not be as important. So like in the curriculum, they use the example of predicting heart disease pretty often, where it's more important that you get, like, you correctly predict. I'm like confusing true and false and positive, negative, and all this. So like when you're predicting heart disease, it's like okay if you falsely flag like some cases, like 25% of them, if that means that, so you get like 25% of your positive predictions are false positives. If that means that you still capture like 99% of all the truly positive cases. There's like a trade-off there. And so for like that instance, like heart disease, like it's okay if you like, maybe like startle a patient like a little bit, but it's really not okay if you completely miss a large proportion of patients that actually do have heart disease. So it's better to, maybe like stun someone into, picking up their cardio, rather than not flagging someone that actually has heart disease and then they get, morbidly ill from it. So anyway, yeah, there's you have to be really clear about what your goals are and what you're trying to predict, and that's going to inform which one of these metrics you're going to care the most about. And of course, if you're in the notebook, here's all your example code for that stuff. So let's talk about ROC curves and AUC. Obviously, they're both acronyms. ROC stands for receiver operator characteristic, and AUC just stands for area under the curve. So, what the ROC curve represents, and this is not the ROC curve, by the way, this is just, I'll explain. What the ROC curve represents is the true positive rate versus the false positive rate, for like various tunings of the model, so to speak. So there's not really like a good way to visualize this exactly with your data. Oh, and by the way, we got our math here for a true positive rate and our false positive rate. Pretty straightforward mathematics there. So what this little blue area represents is our false or incorrect predictions, our false positives and our false negatives, right? Obviously, when this blue area is quite big and we're incorrectly predicting quite often, that's not so good. We want to minimize that as much as possible. So, this is quite verbose, I know. Scikit-Learn in the metrics module has some functions that make this pretty easy for us to calculate. It's ROC curve and AUC. So we're instantiating our model and we're fitting it here. We're calling this decision function, which I need to read the docs on that a little bit more. So we do that to declare this variable y score, and we pass that in along with our actually observed model. So this is y test here, but if it's your final model and you're and you're evaluating like the trained model versus like untested data, your tested data, then my point is that sometimes you would use Y-train here, sometimes you would use Y-test here, depending on what point you are in the workflow. That's going to return to you three things: your false positive rate, your true positive rate, and your thresholds, which is your wherever this like intersect is, right here, your decision boundary, so to speak. Whew. Okay. Styling with Seaborn. Most of this is not my code, actually. Most of this was provided directly by Flatiron, like in the curriculum. Right here, you can see we're calling the AUC function. All we're doing is passing in our false positive rate and true positive rate, and that gives us the area under the curve. The greater the area under the curve, the better, generally speaking. This is going to be on a scale of 0 to 1. So, a good AUC value is going to be like 0.8, 0.85, 0.9, so on. This is all just matplotlib stuff. This study vlog, or even this whole series, isn't really about data visualization, so we're not going to worry about that a whole lot. If you're really curious about it, you can go to the GitHub and check out the notebook. But the point being that we're using this ROC curve function to calculate our false positive rate, our true positive rate, and our thresholds, and we're using the AUC function with the return values from our ROC curve function. And that altogether allows us to create this nifty visualization right here. And so the AUC function is basically giving you what's the total area of everything underneath this orange line here. And I don't have the return value for that AUC function, unfortunately. But so you can see this is basically showing you that as your false positive rate increases, your true positive rate sort of decreases. So I would, depending on what your goals and needs are out of the model, usually you're going to pick the iteration or form of the model that's around like this corner right here. That looks like 0.27 ish. So with a true positive rate of 0.95, which is pretty good, and you get a 0.27 false positive rate. Depending on like my goals, I would pick somewhere around like right here, more than likely. So we can use the ROC curve to compare logistic regression models. You can tune the model in different ways to give you different ROC curves, and that's done by adjusting various hyperparameters. So the hyperparameters of a model are the parameters of the function that you pass in. So I might use the words hyperparameter and parameter here a little synonymously. Hyperparameter refers to like the model itself. We're talking like in the mathematical world when we use the word hyperparameter, versus when you're talking in the coding world, these are just parameters. So when you like instantiate your like logistic regression model, where to go? Right here. There's other parameters that you could pass in here. Well, this is your dot fit function. So like, if I did like, it's not giving me my autocomplete because I haven't actually imported. So when we instantiate like a logistic regression class object, there's other parameters that we could pass in, such as our like regularization term, which is gonna look something like you might have 1, or you might have like 1e to the 5, e being Euler's constant, that sort of stuff. So just like any function in Python, you have parameters that you can pass into it. So to adjust your ROC curve, you have your regularization parameter, your penalty term, which I talked about 1 or 2 videos ago, your class weights, which we'll talk about what that is exactly here in a second. So you remember L1 and L2, that's like your lasso and ridge regression and that sort of thing. So you can adjust all those little things about the model to kind of manipulate and try to optimize against this ROC curve right here, which is what this visualization represents. So you would go through and you would build a few different models, passing in different parameters for different. You would have a number of different logistic regression objects that you would instantiate, and then you would pass different parameters into them as you instantiate them, and then you would fit your data to those various models with different hyperparameters passed into them. So visually, just looking at this, it looks like this red one with it looks like the intercept was fit there, which makes sense because you can see where it intercepts the y-axis right there. It was probably our best one, and so as I'm going through the notebook and I get this visualization, I would go, aha, that's the best one, and I would have some variable name that's like assigned to that particular model, right? And I would pick that one as my final model, and I would go on with it. So all that to say, there's different hyperparameters in your models that you can adjust to optimize against your ROC curves, and your ROC curve is a good way to visualize these metrics that we were talking about earlier. Scrolled a little too fast. So it's just another way of comparing one model against the other and helping you decide like which model to continue forward with. Class imbalance problems. So like I said earlier, there's like a problem of if you have maybe like 100 data points and 2 of them are the ones you're actually interested in, the rest are just kind of there. So if you had, in that situation, 100 data points and 2 that you're interested in predicting, or let's say like the 98 or the 98 out of 100 or what you're interested in predicting, even if you just guessed, if your model was completely random and just guessed, and so it would be like around 50% probability that you get it right or not, so 50% precision, then it would still have like pretty decent accuracy, right? Which is, mathematically might appear as a good model, but it's not really useful at actually making real world predictions. So this is kind of that's what class weights are, is basically what proportion of the total observations is represented by one class or the other, right? So that can have cause some issues with you need like more than like 0.001% of your data to be like a particular class if you're interested in predicting that class, because if most of your data is a negative example of that class you're predicting, then you have like almost no positive examples of it, or not nearly enough to train the model effectively to accurately predict it, right? Like I said last video, I think it was, like, you need positive and negative examples, and you need like a good proportion of both. So to deal with that, we're going to talk about a new function and library here, and this thing called SMOTE, which stands for Synthetic Minority Oversampling. So what SMOTE's basically used for is to create synthetic data for your minority class when the minority, this is specific to when your minority class in your data, the class that has the least proportion of the data, that's the one that you're interested in predicting. So SMOTE is a way to kind of engineer your data to be more suited to train the model. So we have our example code here, and I thought, how weird. Give me one quick second. No, I'm not going to do that right now. Whoops, no, let's not do that. IMB Learn minority. You know what? Here's what we're gonna do. I have the docs linked right here, so I'm going to actually pull up the docs here for that. There we go. Oversampling, that's the module I was trying to think of. Yeah, so this is documentation for it. If you're in the notebook, you can click the link right there. So this code would, I have so many windows. So this code would look, what was it, oversampling? So it would look like that. You would first import it from this imbalanced learning library and reference the oversampling module and import that specific function, smote. This is just to show the comparison. We call our smote function. This IMB Learn library seems to work a lot like Scikit-Learn. Kind of like in Scikit-Learn, you have the fit transform method that you can call on different types of objects. This has this fit resample, which works a lot like fit transform does in Scikit-Learn. So we're passing in our training data, and you can see here that originally we have 213,000 data points for the class we're not interested in predicting, and only 372 for the class we are interested in predicting, which is a extremely tiny percent of our total data. And so smote basically synthesizes enough data so that it is, in this case, 50-50 distribution of the class that we're interested in predicting versus we're not predicting. I believe there's other parameters you can pass in to adjust like the exact proportions. In fact, let me take a look here. Yeah, like your sampling strategy parameter, you have your random state parameter, all that good stuff. Yeah. So that's a really cool and a really interesting tool. If you're sitting there and you're like, oh, I don't have enough data on the class I'm actually interested in, you can sort of create that data using this smote function from the IMB Learn library. All right, so that is it for today's topic review. A lot of cool stuff, a lot of really high-level math things going on in this module. Excuse me. I just ate lunch right before this. So if you're looking in this notebook, you can link to the YouTube channel right here. You can, if you're on the YouTube channel, I'll have this same link right here going to my GitHub. If you want to chat with me or have questions or whatever, you can contact me or connect with me on LinkedIn. And if you're interested in Flatiron School, then I have the link right here. This link goes directly to their data science program. They also have, you know what? Let's just go take a look. Oh my gosh! Wow, 44 minutes. I did not realize this video was that long. Okay, so what's another 5 minutes? So this is their page for their data science program. Kind of gives you an overview of what we cover, and this is an understatement right here. This is like the first week, and then it gets like way more meta from there. So, oh, that's just phase 1. That explains why. Okay, yeah, I'm in phase 4 right now, so you can see we're you're gonna if you've been watching the videos, you're gonna recognize a lot of these terms right here, like hyperparameter tuning. We just talked about that literally in this video. Logistic regression's been like the last 2 or 3 videos. MLE, you talked about that last video. Optimizing cost function, that was like 3 or 4 videos ago. You know, you get the point. I've been saying there's 5 phases. The 5th phase is your capstone project, and it's also your job search. So that's going to be really cool. It's a great school. Obviously, people in the industry agree that it's a great program. You got full-time, part-time options. What I was going to mention earlier is that I'm doing data science. However, they have 4 programs that they really offer: software engineering, data science, cybersecurity, and product design. I've been trying to convince my sister to look into the product design program because I think she would be well suited for it. And cybersecurity, from what I understand, is geared a little bit more towards people that have like some experience in the tech industry, or at least like in IT. So keep that in mind if you're considering applying for the cybersecurity program. Yeah, but the versus like software engineering, data science, product designs, more kind of designed for if you have absolutely zero experience at all. However, I will say for the data science program, it would, if you're seriously considering doing the data science program, I would strongly recommend that you work on your math skills and learn like a little bit of Python beforehand. It's really like learning Python helps, but you can learn Python pretty easy if you've got like a knack for the math. That's one thing I wish I would have done differently preemptively for the program, is like brush up on my calculus and algebra and stuff like that a little bit. Or even just like, basic math skills, like understanding like exponent, like operations and like that sort of thing. Anyway, hope you enjoyed the video. Hope you got something out of it. Click those links down below if you're interested in any of that sort of stuff. Check out Flatiron if you're interested in it. I highly recommend it. I'm having a great time here. And until next time, guys and gals, keep on learning some cool stuff. All right, see you next time.